Good evening, everyone. I, Adya Pandey, welcome you all to the 16th session of PSPO webinar series. Today, we have with us Dr. Minakshi Kumari, who is an assistant professor in operations and supply chain area at Indian Institute of Management, Jammu. Her research interests are majorly aligned to manufacturing sector with focus on various aspects of smart manufacturing. She has received her doctorate from IIT Delhi, and her professional experience is a blend of academia and industry. In her previous experiences, she has headed the research and business analytics division of a Delhi-based startup and has been associated with IIM Ahmedabad as an academic associate in production and quantitative methods area. Today, she will discuss with her work titled Developing a Prescriptive Decision Support System for Shop Floor Control with us. Dr. Minakshi, I request you to begin with your presentation.
Sure. Thank you, Adya. Thank you for this nice introduction. And I'll quickly share my presentation for today. So I hope it is clearly visible to everyone.
Yes, ma'am, it's visible.
Okay. So good evening, everyone, joining in for this session today. I'm really thankful to the Public Systems Lab and the people associated, especially Professor Deshmukh and Professor Bolia, for giving me this opportunity to present my latest research work on designing the prescriptive decision support system for a manufacturing system. This work of mine basically is an extension of my PhD work. I had developed certain portions of it during my PhD, but to make it more realistic and applicable to industry, the extension of a single machine system to a multi-machine system was very, very much needed. So this work actually is bringing together two critical aspects, or rather I would say three critical aspects. One is your design of a support system, which is a simulation-based system. Second is developing a pure prescription design. And third is demonstrating it for a multi-machine manufacturing system. So with this, I would like you to walk you through the flow of the presentation. In today's presentation, first I would like to establish the background of this research problem. And I would like to, formalize why this problem actually needs attention. That part I would like to bring on. And then I would take you to the methodology that we adopted to follow this, to figure out a solution to this problem. Then based on the model that we developed, what kind of analysis we conducted and the findings that we reported will be highlighted. We will also try, or I personally, on behalf of the co-author of this paper, which is Professor Makarand Kulkarni from IIT Bombay, I would like to bring out the contributions, limitations, and the future scope that we have for this work. And at the end, I would definitely like to handle the questions or the queries that you all have. Uh, um, I have kept the questions section at the end of this presentation, but I won't mind if anyone during the presentation also wants to raise some of the concerns. So I am open to explaining the concepts or clarifying anything that is required on the go also. So not a hard and fast rule that we will stick till the end. So let me walk you through a small story which is related to the future of manufacturing. So if you look at the trend which manufacturing nowadays is having, a lot of things like Internet of Things, mobile network systems, wireless sensor networks, design of embedded systems, cloud computing, edge computing, big database decision making. All this is making a lot of, I would say, buzz in the manufacturing domain. If you look at all these dimensions, they majorly focus on one core thing, and that is your data intensive environment. So the thing is, the future of manufacturing says that we will have a manufacturing system which can foresee what all can happen and then try to bake in or try to figure out how these impending things which are coming in the future can be avoided by taking an action plan in the present. So we want to create an environment, or we want to create some kind of an interference mechanism which is developed by taking into account whatever is the historical nature of the manufacturing system and the direction that it will take in the future. So by clubbing these two things, which is the historical pattern and the future behavior of the system, we try to come up with some kind of a control mechanism which can be deployed in the current time, so that the basic requirements of the manufacturing are met, the uncertainties which are impending on the manufacturing system can be avoided in an optimized fashion, or rather to say in the best possible fashion. So at the core of all this is either you go for any kind of an advanced computing technology, you think of connecting multiple devices to reach this agenda or attain this agenda. At the center of it always remains that we will have an information or relevant data that is either collected from the history of this particular system, or at the same time we have some information of how the transition would be happening in the future. So the data is at the core of all this. So this research that I am presenting today is planned to guide the decision maker after the data gatheration or the data collection is already done. So the sensors are already installed. We already have the information of the historical patterns of the system, or at least we have the data of what has been the behavior of a particular manufacturing machine or a system which comprises of multiple machines. So the background is that we already have the collection of data done, and now we try to see how this particular data can be used to create the manufacturing of future, which can assimilate the historical patterns and predict the future behavior of the system. So the background is development of those cyber physical systems, which are real time, responding quickly, averting anything that can go wrong by having a transition of the paradigm, which is like earlier it used to be, we used to have a machine failure, then we used to figure out why this has happened. But now the decision making is making a kind of a shift. And we are now looking at how the behavior can be predicted. And once a prediction is witnessed, how it can be resolved, or how the system can automatically come up with the prescription of the action plan that is to be deployed in a manufacturing system. So the focus of this study has been not on the descriptive side. We assume that the descriptive data is already there. Now we are using it to develop a predictive as well as a prescriptive mechanism. So if you talk about a typical manufacturing system, descriptive info data will always talk about how are we doing currently. So we need to figure out, are our jobs meeting the requirement? Are our jobs meeting the time requirements as well as the quality requirements? Are we having too many quality defects? All this can be very well analyzed through the descriptive analytics. But using the information that is with us, what can be the trend of in the future? What can be the trait of the future? That is what we require to be predicting when we talk about a particular manufacturing shop. So after we have predicted what can happen in the future, the prescriptive analytics should talk about how these predictions can be handled effectively. So the focus, as I said, is on the predictive as well as the prescriptive part. So the research study basically started with this I would say not, rather than going by saying that we started formalizing the prediction part, rather we tried understanding what parameters should we be predicting if we want to control the shop floor behavior. So the first part of this research was finding what needs to be predicted. And second, once the prediction is achieved, how it can be used for prescribing the future action plan. So if you look at the bottom of this slide, we actually went in a very sequential fashion. We tried understanding the behavior of the shop floor, figuring out what needs to be predicted. So we came up with certain parameters which are a representation of the or which are like a probe measure which can be used to predict the behavior of the system. Now we also tried understanding how these predictors can be designed. Is it required to be a single measure approach? Is it going to be a multi-measure approach? Then we tried understanding which shop floor characteristics need to be translated into this prediction scheme. Is it going to be one or two factors? Are there more number of factors based on which the prediction has to be designed? And we then tried figuring out what is the difference of this prediction come prescription mechanism for a single machine system, and how the behavior will change if we move to a multi-machine kind of a system. So moving on, to make you more related or the concept more relatable to everyone present here, I would like to establish the problem complexity first. So let's assume a machine. The machine has an equipment health index, which is green when the machine is completely healthy. All the components are working as per the plan, and preventive maintenance has also been done as and when required. But as we move or as we keep on producing on this particular machine, the machine health gradually gets changed and it moves from green to blue zone and ultimately it goes to the red zone. When the machine is in a healthy condition, and the production manager as well as the maintenance manager is looking that there are chances of machine getting into an unhealthy state, they tend to have a planned maintenance scheduled. Now if there is a maintenance planning done, the production manager will coordinate with the maintenance manager. The maintenance manager in turn will connect with the personnel required for this maintenance activity, the third party service provider requirements if any, and in case if there are spare parts requirement also. So there is a lot of coordination happening at the back end. But in the meantime, there happens a situation where there is a rush order that comes into picture. And as a result, the planned maintenance has to be cancelled. And the same information now flows to the maintenance head, all the connected parties. And as a result, the maintenance rescheduling happens and we schedule it sometime later, let's say. So after this rescheduling is happening, we have, just a second. Yeah. It could be that the rush order is getting completed before the maintenance rescheduling, but it could also be a situation that since we have rescheduled the maintenance, there is a breakdown in between. And as a result, neither the rush order could be met, neither the other jobs which could have been prioritized or which were already in the queue of the machine, they could be produced. And as a result, we have a loss of order as well as customer goodwill also. So this is one scenario. But if we talk about another scenario, in case if there is a rush order that we have achieved or received, and the maintenance has been rescheduled, and there has been no breakdown. But since the maintenance has been rescheduled, the quality of the product is going down. So either the machine has gone down because of the pushing of the maintenance schedule, or the quality of the product has gone for a toss. That's what we can say for a change in the maintenance schedule that is impending. So as a result, this is just one scenario. This is one uncertainty which the shop floor is subjected to, and that is just by due to changing the scheduled maintenance and on the receipt of a rush order. But if you talk about a typical manufacturing scenario, there are n number of other uncertainties also which come into picture. And we first tried understanding what these environmental variables are, which result in lot of complexity of decision making in shop floor. So we came up with this indicative list of 15 uncertainties. There are chances of due date change. There could be a probability of due date deferment. It might get extension. It can get expedition also. We say that the job is to be delivered earlier. There is an uncertainty in the magnitude of the due date change also. And as a result, as I said, we can have a deferment, we can have an expedition. The other issues related to quality could be setup change failure, process change, batch size increase probability, then the magnitude in the batch size, it could increase or decrease. Then comes the priority change. And in case if there is a failure, there are uncertainties associated with the maintenance time also. So we can have an average corrective maintenance time variability, and at the same time, we can have availability or unavailability of the maintenance personnel also. And in case if we require some spare parts, we might require to arrange for maintenance personnel along with the spare part that we need to replace. So these were the 15 list of uncertainties, as I said, indicative ones, which we could figure out from the high pressure die casting unit where I had done this research at. If you change the manufacturing system, there could be some other uncertainties also which can come up, and some of them might be dropped in depending upon which manufacturing system we are referring to. So after we figured out that these are the uncertainties, the first thing that came to our mind was, if because of them, the complexity of decision making is increasing, why not start with one kind of a measure, which is complexity itself? So we predict that as a predictive measure, why not choose complexity only? So if a manufacturing system's complexity is dependent on these factors, the first probe measures or the predictor that we identified was complexity in itself. So as I said, we started planning with the predictive measures. The first thing was, will I be able to meet the customer orders as per the schedule while meeting the desired quality standards? So as a decision maker, we started looking at this problem. What are the questions that the shop floor manager generally faces? So first question is, whether will I be able to meet the customer orders as per the time as well as per the quality? There could be a case where I meet the timeline, but the quality is not met. And in case if I fail to meet the desired production order, either in time or schedule, what would be the disadvantage, or what will be the penalization for me? And the third question was, even if the complexity is low as well as the penalty is low, is the situation still desirable? This was the third question that we came up with. So as I said, we started first of all by looking at complexity as the measure. We looked at the literature, how complexity has been modeled. But I would say the existing literature of complexity modeling always talked about probability of machine being available or not available, just using these probability data. But we realized that that could not be some kind of a probe measure which can be used always, because if a machine is down, how is it serving the purpose? If it is up, how is it serving the purpose? In both the cases, the purpose is of meeting the customer order. So we looked at revising or giving a new dimension to the thought of complexity modeling, and this was our first measure. But as we moved forward, we realized that complexity is dependent upon certainty as well as uncertainty. So if you are very sure of anything, then your complexity is very, very low. Even if I know that my machine is going to fail, that is a certainty of information that I have, and as a result, the complexity is low. Complexity is highest when we have 0.5 probability of anything, any outcome coming up. So whenever the probability of equal outcome, or two outcomes, let's say, with equal probability exists, the complexity is highest. So complexity is something which can be low on the either side of the continuum. Even if I am 100% sure, even if I am 100% unsure. If I am in between sure and unsure, then only my complexity is high. So identifying which complexity is good, that was the next thing which resulted in coming up with another predictor, and that was your penalty. We tried understanding what could be the complexity relation with the cost part, which wherever the penalty is high, we will say that this is something which should be given proper attention. But later we realized that there is not only the tangible aspect that is impacting the decision making, and as a result, we should have third probe measure which takes into account the intangible aspect of decision making, and that is desirability. So even if the complexity is low and the penalty is low, the decision maker may not be choosing that path, or that may not be interested in going by that kind of a rule. So let's say I'll give you an example. If we have lot of time with us for a job to be delivered, the due date is far off, and as a result, the penalty is low. And since the due date is far off, even if the machine is failing, I say the complexity is low. So the desirability that way is telling me that penalty is low, complexity is also, let's say, low. But would I be like, or as a decision maker, would I like to be in this state where my machine is sure to be failing? So that came, or that gave the idea of third measure, which is desirability. So these were the three measures that we modeled. And for complexity, this is the standard formula that has been used for ages for complexity modeling. But in our case, the representation of Pij, the probability here is not of of a machine being in a idle state or a working state. Rather, we have tried calculating the probability of a job in the queue of a machine to be on time as well as per the quality. So we said that a system's complexity is dependent upon the number of jobs that are in the queue and also the number of resources that are present in any manufacturing system. So Pij here represents the probability of a job to take a particular state in terms of schedule and quality combination. So the other measures that we modeled were complexity along with penalty and desirability. So I am walking you through quickly through the model. So we figured out that in any job processing, we would require certain setup time, certain processing time, and each job will be given an early due date as well as a late due date. And the completion time of a particular batch would be dependent upon what the processing time is, which is multiplied by the batch size, and then on each of them we sum total the setup time. So a job which is completed before the early due date is said to be an early job, and anything which is like between EDD, which is the early due date, and late due date is referred to as your on-time job. And in case if it is more than your due date, obviously it's a late job. We looked at these schedule states and the quality states. We came up with the combinations of what could be the probable combinations of states. And there are 6 combinations that we came up with. And early good, on time good, late good, early bad, on time bad, and late bad. So if you look at these 6 states, on time good is the best one. But if you talk about early good, it is relatively better than being late good. So this is the relative ranking that we used for modeling the desirability as well as the penalty part. So if you look at these state combinations, we tried simulating the behavior of the system to figure out what is the probability of a job falling in any of these 6 combinations, and using it we tried to figure out the complexity during the simulation phase, which is the duration of the simulation. That could be 1 month, 5 months, depending upon whatever kind of a manufacturing system you are referring to. Then we came up with a penalty formulation. We said that a high priority job will have a different penalty. However, our normal priority job will have a different penalty, which will be sum total of the penalty, which is related to the schedule as well as the quality problems. So phi is something which we used as a parameter, which is a coefficient that can be used in different scenarios. We came up with linear format. There are chances we can we can come up with the values from the real life scenarios by using the data and then decide on what this coefficient can be. So using this, we calculated the total penalty of the system. But as I said, we can have different penalty value, different complexity value, and depending upon that, we would try to find what the desirability of the system is. So we chose, we looked at what state combinations are there, and we awarded them values. Like if a job is on time good, we will give it an index of 6. That's the best performing one. If it is late as well as bad, this is the worst performing job, and that will be given a index of 1. So the probability is now multiplied with these desirability values, and we came up with the desirability modeling for this particular machine. So the simulator that we designed was of this nature, where we identified the environmental variables, and we had the data for them. We tried figuring out what the past of this system has been. Based on that data, we superimpose it on the present shop floor scenario and try to figure out what the future system state could be. And this gave us the projected measure values, or we came up with certain indices which were complexity, penalty, and desirability. So the environmental variables are the 15 that we identified. The baseline here refers to what is the currently prevailing situation on the shop floor, and the currently prevailing shop floor situation was generated or simulated by certain parameters, which was what is the batch composition in the queue of the machine. When I say batch composition, the reference is to the combination of early, on time, and late batches. And then we have batch characteristics like what is the volume size, what is the processing time, setup time, all this. And then we also tried to look at what are the machine ages that we have modeled, and in case if we have any maintenance schedule on them. And then we assumed certain prevailing levels of environmental variables to simulate the behavior of the behavioral pattern and project the effect on complexity, penalty, and desirability. So this is the internal architecture of the simulator design. These are the multiple components of the simulator. We simulated an component failure simulation part where we tried, modeling the system as an n component system. We looked at time to failure of each component. We simulated that using Weibull distribution. And then we, after the maintenance is done or replacement is done, we revised the component age, and we said that the machine failure time is equal to the most likely failure time of the one of the components which is nearby in the future going to fail. So using this, we tried to model the failure part, and then we came up to the simulation of the mean repair time, where we said that if the system fails, what is the corrective action we have taken, how much has been the lead time, the variability in the lead time. Then we have also simulated the range of probabilities for spare unavailability and the maintenance personnel unavailability. The other components we simulated were chances of setup success, process shift, due date change, and batch size change. Along with this, the last part that we have simulated is the priority change. We assumed that out of 100 jobs that, or it was not basically an assumption, rather when we looked at or observed the high pressure die casting system, we looked at a pattern that out of 100 jobs that are received on the floor, what is the probability that the priority of a particular job changes. So using those shop floor data, we tried figuring out the parameters or estimates of those distributions and then used it to simulate the behavioral pattern of the manufacturing system. So the reference system which we used was a high pressure die casting unit, and these were the components which we modeled, and we used a maximum likelihood estimate to model the shape and the scale parameters for these 26 components. So I have been asked time and again about these 26 components. Although the component count is quite exhaustive, but we identified those critical components only, the failure of which was resulting in a lot of issues with the machine. So we restricted it to 26 because we wanted it to be a solvable sort of a problem also. And at the same time, these were the 26 critical components where the failure information was available readily, and also they were the most critical ones. So this is the input reference system that we have used, and this is the analysis methodology that we have used. So if there is a shop floor manager, he will have jobs to be processed on the machine. Each one of them will have certain combinations of early, on time, and late jobs. They will be subjected to certain uncertainties. And then we will try to see what is their baseline complexity, baseline penalty, and baseline desirability. Then we simulate the future behavior, changes in the complexity, penalty, and desirability. If it is more than 10% plus or minus, we say that this particular uncertainty or this particular environmental variable needs an intervention. It can be related to maintenance, it can be related to quality, it can be related to scheduling, or multiple combinations of them, all of them also. So this was the basic experimental design that we did. We had combinations of early, on time, and late jobs created. And we also came up with a variables level, which was all variables, all environmental variables at their low levels, at their medium levels, and all the variables considered at high level. So this gave to the way to the single measure approach. But if you talk about the multi-measure approach that we have been discussing so far, which is based on complexity, penalty, and desirability, if we use these three measures for each of the machines, the decision making becomes very, very difficult. Monitoring three parameters for each machine is difficult. So we came up with an idea of combining these multi-measure approaches, and we came up with the idea of making them into one unified index. So the next question was, how do we unify them? So when we looked at the behavioral pattern of these multi-measures, we realized that each one of them at times is behaving in a correlated fashion. Sometimes their correlation goes off. And then the second thing is, we needed some kind of an automated decision making, which can combine these parameters by taking these parameters themselves. We don't require any external intervention. So the machine is throwing certain parameters out, and those probe measures can automatically talk to themselves and come up with a priority for each one of them, and then combine them into a unified metric. So for that, we tried looking at certain multi-criteria decision-making techniques, but the only criteria which can be used in automated environment that we could identify was a critic approach, and we used it to combine these multiple, uh, I would say multiple measures into a single unified measure. So critic has a standard process flow. We followed the same. I'm not going to discuss the critic MCDM technique in detail. Anyone who is interested in this can refer to some of my research papers also. But otherwise, I would just like to talk that we used this particular technique because it was an automated kind of an environment. And this was the final unified index that we calculated. So using it, we came with a single measure approach. Same way, we tried simulating certain environments of shop floor, and we came up with the weights for each of these criteria. And the same approach of prevailing shop floor scenario, futuristic shop floor scenario, any difference which is more than plus and minus 10% was the factor that we identified as significant one. So moving on, I'll skip this part and move to the multi-machine configuration in the interest of time, because I see Adya, please alarm me if I am overshooting the time. Okay. Okay. So I think I am within the timelines.
Actually, we are beyond the timelines, but we can continue.
Okay, okay. So I'll try quickly wrapping up through the multi-level predictive control mechanism. So as we move from a single machine system and move to the multi-machine systems, the configuration actually it gets more complex. And as a result, going by one or multiple metric also becomes difficult. So someone who is on a shop floor and is looking at one machine, his idea, his or her idea of the machine in control or out of control would be different, while somebody who is a decision maker, who is like a manager seated in CMD's office, his idea of system being in control or out of control would be different. So you have to look at a system perspective as well as a machine perspective. For a shop floor manager, every machine that is on the shop floor has to be in control, then only his system is in control. But somebody who is looking at a multi-machine system configuration, the hierarchical decision making nature structure changes. So keeping this in view, we tried coming up with a multi-machine model. We identified environmental variables which we tried splitting into two categories. There were some parameters which were having pronounced effect on the system level only. However, there were some of them which were more prominent or more specific to certain machines, and we tried categorizing them. And this is the system level simulation that we did. We said that there are a number of batches that are arriving into a system. Each batch can be going into any machine's queue, and whichever machine it goes into, we will look at the effect on the or the uncertainties of that machine will become more pronounced on that batch, and we will look at what the effect on the predictive measures are happening. So using this, we created a system level simulation blueprint and observed the predictors. And we used the same model to have a machine level simulation created. We had n batches, but not all of them are going to a simple machine or single machine. We are sending them to a different batch proportion to multiple machines. And then there are system level uncertainties and machine level uncertainties that we have superimposed. Again, we tried identifying those predictive control approaches. So after identifying these predictive approaches, I'll just walk you through the prescription design. We identified that through the predictive measures, we identify that whether quality needs intervention or maintenance leads to intervention, or both of them require some sort of an intervention. So in case if it's maintenance, we will impose a maintenance intervention scheme. If quality requires intervention, we will impose the quality intervention scheme. And if both of them are having certain issues, then we will have combined or joint maintenance plus quality intervention. So after these interventions are imposed, again through a simulation model, we look at the effect of these intervention both at machine level as well as the system level, and we came up with a comparison of what if we go by multi-measure approach, what if we go by single measure approach, and then using it we come up with a control scenario like if it is a maintenance related decision or intervention, the prescription says that change component number 6 within 15 days and repair certain other components. This kind of a prescription is generated. If it is quality, then the intervention could be that your sampling plan needs to be changed. The kind of proportion that you are picking for your sampling, that needs to be changed. So as Adya is saying that I am overshooting the time, so I'll stop at this design of prescription mechanism. Anyone having any questions can feel free to ask me.
Request everyone to raise your hands in case of any queries. We'll take them up one by one.
So no questions?
Can I ask a question?
Yeah, sure. Why not?
Yeah.
Hello, sir.
Minakshi, a very interesting presentation.
Thank you so much, sir.
Yeah. What I was wondering is, finally, of course, I came to know that there's a single machine, and then you have taken more machines into consideration. Now,
Yes, sir.
when it is a single machine case, are you also looking at the way the jobs are sequenced, like the shortest processing time rule and other things? Were they still applicable? That the shortest processing time rule is still the best?
Yeah, so the release time, the job release, during the release time only, we had sequenced the jobs. But after we looked at the high pressure die casting unit, the uncertainties were more prominent when it comes to maintenance and quality issues. So the intervention plan was not done for the rescheduling or scheduling part, but the initial sequence we generated was used, but developed by using these SPT rules only.
One other thing is that usually whenever breakdown occurs, the person who's supposed to be the maintenance guy is away from the scene to the canteen or something. When he
Yes,
is there present, the failure does not take place.
true.
Was that a realization also in your case?
Sir, I would say that that realization was so frequent, but the problem was that machine was not an Indian made. So the component replacement time was taking lot, it was longer. Reason being we had to, order, they had to basically order it from some other part, some other nation at times, Japanese
And the,
company.
and the other thing about the spare parts, was there any combination of VED and ABC analysis so that if it was a C-class vital item, that there should be no shortage on that count and all that?
Yes. So they have worked on those models, but doesn't work so effectively. They have planned for it, but most of the time there are certain, like if they plan the inventory for those which are identified, in this
Yeah.
cycle it is working well, but in the next cycle some other component becomes crucial.
And one last thing from my side, when you talk
Yes,
about simulation, you
yes,
are
sir.
saying you tried for 1 month or 2 months or 3 months. But how long should that simulation run be?
Sir, for my experimentation, actually, I had done it for 1 month, 2 months, till 5 months. But if I talk about reactive control, that too looking at the futuristic data, the more realistic would be to simulate it for at max 30 days. Because if I am simulating beyond that, probably I am overseeing or giving more chance of uncertainties to come up. So real-time control with a limited view towards the future. So my take is that we should look at 30 days time, idealistically.
And Weibull distribution is still being holding true, or is it having its own limitations?
Sir, I think for maintenance, viable distribution is relevant till maintenance is there. Reason being, we have those useful life, increasing failure rates, and then decreasing failure rate cycles. So the nothing models the failure pattern so well, better than Bible. So that's where I think Bible is making more sense.
Conventionally, Bible is the best.
Yes, sir. Yes.
Anyway, thank you very much.
Thank you so much,
very
sir,
impressed
joining
with your
in.
modeling, and I think good of Kulkarni and you to come up with a nice presentation. Thank you very much.
Thank you, sir. Thank you for joining in.
We have a query from Shivam. Shivam, please go ahead.
Hello, ma'am.
Hello,
So I need to ask that is there any order of analyzing the measures which were complexity, desirability, and penalty?
So I would rather ask you a question. If I am predicting something, will I be waiting for the next probe measure to be known to me? The better option is to look at
Absolutely.
all three of them together.
Okay.
Correct. But
Simultaneous.
we came up with these measures in a sequential order, because when we tried just working with complexity, we realized that complexity can be low on either side. So let's look at something else. But then penalty came into picture, but that was taking into account just the tangible part. So there we came up with the third measure, which was desirability. And if you look at the modeling side also, the inputs remain common. The probability of state. So I hope I answered you, Shiva.
Yes. Yeah.
Okay. Is there any other query from anyone?
So do we also have taken interaction effect of some other variables?
So we assumed them to be, there are some of them which are interaction effect, and that's why the correlation is coming into picture. And that's where critic becomes a handy tool to join them together. So if you look at the critic as a method, it says that if the variable nature is correlated and at the same time, in some phases, it becomes uncorrelated, that's a better choice to go for. So that's where we came up with critic. So what interaction effect you are referring to is like in the design of experiments part that probably you are referring to. We created those.
Yes.
Yeah. So we, in fact, before creating or deploying this simulation model, we had those DOE based, design created for entire pattern of experimentation that is to be done. So that is taken care of when we came up with the experimentation plan. And I would also say that the timeline given is very, very short. So I might not have been able to explain all those technicalities. But in case if anyone is interested, you can look at my papers also. And I would also be personally interested in interacting about my research work.
It was a nice presentation.
Thank you.
So I don't think we have any other queries. So in case of no further queries, we can end the session now. Thank you, Dr. Minakshi, for such a detailed and informative presentation. And I would also like to thank Professor Banwit for joining the session.
Thank you.
I'm really grateful to Professor Banwit for joining in today, and also all those who were present. And thank you, Public Systems Lab, for giving me this opportunity. Thank you.
Would request the team.
Still at IIM Jammu, right?
Yes, sir.
Minakshi.
Yes,
Good.
sir.
Good luck. Thank you.
Thank you, sir. Thank you so much. Yes, sir. Adya, can I sign off now?
Yes, ma'am.
Thank you so much. Thank you, everyone.